Our next presenter is a principal security engineer for Codenomicon. He enjoys breaking software, all of us do, right? He's the author of books about cryptography, mobile application development, as well as Lego robots, which is really cool, and pregnancy.
Separate books.
Very well written. Please welcome Jonathan Knudsen.
Thank you. So my title is Principal Security Engineer, but as you know, titles are both free and often misleading. So I actually wear a few different hats at Codenomicon. This is my presenter hat. I wore a tie today. Is there anyone else here with a tie on? Anyone? Nope. Yes. But so you wouldn't think I was a tool, I wore my blue jeans. So the talk today is about Heartbleed, a little thing you might have heard about in the spring. And it's getting a little old, honestly, for us to go around boasting about it. We just finished putting it on all of our t-shirts and all of our banners and everything, and you know, to be honest, it's getting a little old for that. But what I want to talk to you about today is software testing and how better testing can help find the next Heartbleed, because there's always going to be a next one. There was a next one a few days ago. I don't think we've seen anything quite as spectacularly, totally bad as Heartbleed since then, but we will. It's just a matter of time. So what I want to go through is I'm going to start out with a kind of a gritty discussion of Heartbleed itself, because everybody's heard of it, and most of us kind of know what it is, kind of. But I think a lot of people don't really understand it all the way down at the bits on the wire. And so I'm going to talk about that a little bit, just to explore exactly what this vulnerability is. And then I'll be talking about the general problem of managing software vulnerabilities, which is really what happened here. There was a vulnerability, and nobody found it for a long time. And why is that? And how can we do better? And then I'll be talking about some of the vulnerability management tools that are available, the types of tools that you can use. And then finally, sort of what do we do now? So Heartbleed, the way I think about network protocols is like a script. Like if this were a play, Shakespeare in the Park or something, this is the script for a TLS conversation. And it starts out where the client says, hey, here I am. I want to have a TLS conversation with you, and these are the cipher suites I can speak. And the server writes back and says, oh, okay. Well, this is the cipher suite I want to use, and here's my certificate. And we'll skip the part in red. The client says, okay, checks out the certificate, and they negotiate an encryption key for that session, and then they start talking encrypted to each other. So at some point, somebody said, gee, wouldn't it be great if we could run TLS over datagrams, over UDP, instead of just TCP? And so they made this DTLS thing, and mainly to support DTLS, they introduced this heartbeat message. And the idea was either side could send this heartbeat at any point in the encrypted conversation and get a response, you know, like, are you there? Yeah, I'm still here. And that was the idea of heartbeat. I was trying to remember the RFC number. There's some RFC that specifies the heartbeat message as an extension for the TLS protocol. And that RFC said, well, these heartbeat messages should really be in the encrypted part of the conversation. So that would be, here we go, everything down here and later. And the client could send a heartbeat to the server, and the server could send a heartbeat reply back. But that RFC did not mandate that. And so the way it was implemented in OpenSSL was that you could do heartbeats before the encrypted part, during the unencrypted negotiation part. And so here is one example of what that might look like. So the client and the server are doing their hello messages, and then In this unencrypted negotiation part, the client says, oh, sort of pokes it, pings it. Here's a heartbeat message, and the server responds back. The actual format of this message is the client says, here's my message that I want you to echo back to me, and here's how long it is. And the server says, okay, here's your message right back at you. So the problem is, what if the client lies about the length of the message? So the client sends a message which is 4 bytes long and says it's 36 bytes long. Well, the bug is the server never checks it, right? It says, oh, okay, thanks for that 36 byte message, and here it is, right back at you. And so it sends the message back, the 4 bytes, along with 32 bytes of memory contents, whatever happens to be there. Could be usernames and passwords from previous sessions, could be the server's private key. And the worst possible case of this is that as a client, I say, here's my heartbeat message. It's really 0 bytes, but I say that it's 64K bytes, and the server gladly spits back 64K of its memory at you. It's kind of a perfect storm of terrible stuff. And so it's really easy, because this is all unencrypted, and because it's so easy to craft these messages, it's really easy to script this up. You could spend an hour in Python or whatever and script this up and write a nice little exploit that will just keep on pulling down 64K bytes from the server. You don't really know what's in there, but it's pretty easy to check for the private key because you already have the public key from the server. And so all you do is you just scan through that 64 bytes, 64K bytes of stuff, and try each possible private key and see if it matches up with the public key. And there's some straightforward math that allows you to do that. So here's the source code. This is where the bug is in the OpenSSL source code. Can you see it? It just jumps out at you, doesn't it? So here it is. The first highlighted line there, we're pulling out the length that the client reported to us. Are we putting it in a variable called length? No, we're putting it in a variable called payload. That's another rant though. The second highlighted line is, okay, we'll allocate a buffer of that size. And then the third line is the real bug, is the mem copy. So we're just copying into the return message, and we never check the length, and so we're including basically uninitialized memory, or memory that's previously been used. So like I said, Heartbleed, in terms of a bug in C, it's really no different from any other bug in C that you might see. There's just a line here or there that's not right, and it's not at all obvious when you're just eyeballing it. Why was this such a bad one? Well, the developer made a mistake. Developers always make mistakes, and I'm not busting on developers. I love developers. I used to be a developer. Even the best developers who have been doing this for 35 years are going to make mistakes. And so if you want to improve this, you have to improve the process that surrounds them, that's involved in creating the software. But the developer made a mistake. This was peer-reviewed code. So there was a lot of press about the developer, some poor guy in Germany. I'm sure he felt like he was getting lots of thanks for volunteering his time to work on this thing. There was a peer reviewer who just totally missed it. The code's kind of hard to understand. It could be simplified. It's old code, it's got a lot of backward compatibility built into it. So there's some work that could be done there. But these are volunteers. Yeah.
Is anybody blaming the standard?
I don't know that anyone's blaming the standard. I think, I don't know, from our perspective, we're focusing on the SDLC really, how the software is created and especially tested. And of course, it's open source. These are volunteers. They're not getting paid to do this, as far as I know. And so I don't think it's really fair to put whatever ridiculously high percentage of the world's software, having it depend on this thing that's not being seriously tested. I understand there is now some sort of initiative to do better testing around OpenSSL as well as other open source projects, and I think that's a great idea. It makes a lot of sense, especially given our dependence on it. We don't really know what kind of testing happens. I'm sure they have a lot of internally developed conformance tests at the very least, but we don't really know what they have in terms of negative testing. And then one of the big ones, why this was hard to find, is that OpenSSL doesn't do memory allocation in the standard way. It has, I don't know exactly, I think it's got either some enhancements to the standard memory allocator or it uses its own, and so that made this bug hard to find as well.
I read that the motive for using the non-standard allocator was that it was just dog slow on some computers.
Yeah, I heard performance was the motivator there, so they were trying to just make it run faster. And then finally, there's this thing about the heartbeat being pre-encryption. It would have been harder, not that hard, but it would have been harder to exploit if heartbeat had only been post-encryption. So all of these things kind of came together and resulted in this bug that was just kind of a ridiculous severity. So the thing that really blew my mind was this thing was wandering out in the wild for over 2 years, right? March 2012, and we're all tra-la-la-la, we're using OpenSSL, yay, and then finally April 2014, a guy at Google finds this thing. Independently, we find it like, I don't know, a week and a half later or something. And then eventually, of course, OpenSSL team got a little freaked out that I think not one but two people found this thing, and so they released the patch and the advisory and everything. And I'm sure everybody's got conflicting statistics about how many people are using OpenSSL, but our estimate is there's about 60% of the market, or there was at the time. So tremendous impact. So the challenge is, how did we not notice this? How is it out there for 2 years and nobody noticed? Because it's really kind of a simple thing, and it's simple to exploit. And so how could we have missed this? How do we not do it again? There are three answers to this question. The first one is better testing. We have to do better testing on software. And that's kind of true across the board in software development, where the traditional life cycle is all focused on functionality. So if you're going to make a piece of software, you have designers that make a specification with requirements about how it's supposed to work. You have developers that write code to meet those requirements. You have testers that write tests that make sure those requirements are met. But it's all positive testing. It's all functional. It's all, let's make sure it does what it's supposed to do, that it works. And what needs to be added there is negative testing, which is, let's beat the crap out of this thing and see if it fails. Let's make sure that it doesn't not work. The second approach is better testing. The third approach is better testing. That's what we need. So for people who build software, this is changing. We're kind of at an inflection point in the industry, but the process has to change. So everybody's got a software development lifecycle. You have to adopt a secure development lifecycle. There are a few different elements to that. There are security-based considerations built into the very beginning with the design of the thing and making the requirements and so forth. And there's security analysis that you do on the design way up front. And then that also involves negative testing, to make sure that the thing that you build is robust and secure, or as robust and secure as it can be. For buyer organizations, anyone who uses software, people who buy equipment or pieces of software to do their business, you have to ask for better from your vendors. You have to. Demand better from your vendors. And one way you can do this is, well, hey, I'd love to buy your product because I really like the features, but what kind of secure development lifecycle do you have? What kind of robustness and security testing did you do? Hold your vendors accountable. So the general problem is managing software vulnerabilities, and it's a big problem. And this is actually a subset of a larger discipline, which is risk management, which I never want to get into. It's like fortune telling and trying to augur the future. You're supposed to.
It is black art, but not fortune.
Black art, then, because you have to sort of make up numbers for the amount of risk inherent in things and the likelihood of something bad happening.
It's selling insurance.
Pretty much. You make up a bunch of numbers, you multiply them together, you get some answer, but all along the way, it's a little fishy. But anyway, in terms of managing software vulnerabilities are in three categories. There are design vulnerabilities, configuration, and code vulnerabilities. And design vulnerabilities is something where the software was just designed badly. Like if I decided to make a website for a bank and I didn't think authentication was necessary, that's a design vulnerability. And my coders can go build it and my testers can test it, but just the design itself is flawed. It makes it vulnerable. Configuration vulnerability is, either you didn't change the default configuration, or you did something stupid and left a door open that you shouldn't have left open. So maybe if you get your banking web application, but you leave the admin credentials at the default, that's a configuration vulnerability. And then finally, code vulnerabilities are the ones we're Codenomicon's most interested in. These are the mistakes made by a programmer that may be exploitable, might not be, but they're bugs. They're bugs in code. And so to improve the security, your security, to lessen your overall risk, you find as many vulnerabilities as you can and shut them up. You fix them.
So in this case, you have a situation where you basically had an open source library that a whole lot of people reached out and grabbed because they didn't want to pay license fees or royalties or whatever you want to call them. And they wanted to lessen the cost of the product.
I guess so. I mean, I think they went out and grabbed it because it was convenient. And I wouldn't expect there to be commercial TLS implementations that were really any better. But go ahead.
But for whatever reason, I mean, where does the fault lie on identifying that? Because they're going to say, well, gee, that was somebody else's implementation of the SDLC. So I'm going to accept them on faith. So
that's the fault, is faith, yeah. So if I'm a major software manufacturer and I want to implement my product and I want it to support TLS, sure, I'll go grab OpenSSL because there's no point in me reinventing that. But I should not accept it blindly. I should test the poop out of it until I'm satisfied that it at least meets my internal requirements.
And what do we do about all the appliance manufacturers who use SSL to protect their access?
Appliances like
Cisco routers, firewalls.
Oh, demand better from your vendors. Ask them what kind of testing they've done. Because I mean, as a builder, like a Cisco or anybody else, if you're pulling in third-party code, it doesn't matter if you wrote it or not. It's your name on the box. You are responsible for it. You know.
Can you talk a little bit about how Codenomicon discovered this vulnerability? Because
Yeah, I'll get there.
One of the things that concerns me about vulnerabilities like Heartbleed is it's not a vulnerability that causes a crash or anything that's very obvious when it fails. So there's a lot of post-test analysis that has to be done. It's like, oh, I sent this type of packet and I got a large amount of data back that I really didn't expect, but it didn't really cause any issues on the server. There was nothing really obvious that had happened. How do you find issues like that?
And there are really two problems here. The one is nobody was testing OpenSSL that thoroughly. I'm sure there was testing being done on it, but I'm sure there should have been more. And the other problem is basically all the existing test tools would not find Heartbleed. And so we were working on a new feature, and that's how we found it. And I'll talk about that, how that happened. So there are some things that you really need humans to find, unfortunately. And most of these are the design and configuration vulnerabilities. There's really no meaningful way to have a machine find those types of vulnerabilities. So what does this mean? This means that you have people who actually sit down in a room and go through the specification of the software and make sure there's no problems there, and look at the configuration and think about possible attacks. And it's all, wetware work. It's all got to be done by people, almost all. And then, to a certain extent, humans can also find code vulnerabilities, but often it's not a very, it's a slow process. So the traditional things are pair programming or code reviews, where the dev team gets together and actually walks through the source code and looks for stuff that looks bad. And it's painful and it's slow, but people find things that way. So it's a viable technique, but it's tough. And then where machines can help us, partially, I would say, in configuration vulnerability searches. So if you think about a tool like Nessus, that's basically hunting down configuration vulnerabilities. Things where you left default passwords, things that have ports open that shouldn't be open, old versions of software, which I would essentially categorize as a configuration vulnerability. So there's some automation to be done there, but I still think humans need to be involved. And then with code vulnerabilities, there are some automated tools that can really help you out a lot. So I'll talk about three main categories of tools. The first one is source code analysis, and this was kind of the leading edge of the curve in automated tools for finding unknown vulnerabilities in software. And the idea is you take all of your source code and you dump it in here, and it goes through, and based on what it knows about your implementation language, usually C probably, it will flag things for you that it thinks might be a problem. Like, I don't even know, like here's a statically sized buffer, and here you've copied without checking the sizes and stuff like that. And these tools are effective. One disadvantage is that buyers cannot use them because they don't have the source code for whatever it is they're trying to look at. So if I'm a hospital and I want to buy an infusion pump that goes on the network, and I want to assess my risk in using this device, I can't use source code analysis on it. But nevertheless, it's a viable technique. It's been around for a while. It does produce results. It tends to produce a long list of things that it thinks might be a problem, which means that then you have to have your developer or development team go through the list and evaluate them and see what they think is a problem and what might not be. Static binary analysis is a relatively new kind of technique, and tools have been around. You could kind of do this manually, but it would be slow and tedious. And so there are now automated static binary analysis tools. And what they do is they take executable code, be it an actual executable file or a library or a firmware image, and they'll go through and slice and dice it and give you a list of the third-party libraries that you used to build that thing. And then you can do nice things like you can automatically correlate that to what the CVEs are for those libraries. And so you don't need the source code, you just need binaries. So from either a builder or a buyer standpoint, you can use an automated static binary analysis tool to go and take a piece of code and know what the libraries are that were used to build it, and know what the library's vulnerabilities are, which might be exposed in that product. So a simple example would be if I take my cable modem firmware and do this kind of analysis on it, maybe it's going to tell me it's running OpenSSL 101C or something I know is vulnerable to Heartbleed. And that would be kind of a red flag for me as a buyer. And then finally, there's fuzzing. And some of you have heard me talk about fuzzing multiple times, so you know I'm a fan. Fuzzing's also good for builders or buyers because it's a dynamic testing technique. No source code is required. And like source code static analysis, the purpose of it is to locate unknown vulnerabilities, the bugs that you do not know about, your 0 days, so that you can find them and fix them. There's a wide range of fuzzing out there, a lot of different techniques, and the basic thing is you want your fuzzer to be able to look legitimate to your target. So if your target is expecting TLS, you want your fuzzer to be able to generate correct TLS messages or almost correct TLS messages that are just messed up in some way. And by providing input that's almost right, but not all the way right, your fuzzer gets the best penetration into the target and it does the most effective testing. One of the big challenges of fuzzing is what we call the Oracle problem, the Oracle challenge, which is, as this gentleman was kind of pointing out, how do you check for failure? The thing about software is that it fails in so many different ways. So sure, if you crash a process, that's pretty easy to notice. If you kernel panic something, that's pretty easy to notice. If you do something subtle, like you send a bad message and you kick off a busy thread and it gradually eats up the available RAM, that's harder to notice. You know, eventually the machine will probably grind to a halt, but going back and figuring out what happened is going to be tough. If you send messages and the target responds to you with the contents of its memory, how are you going to detect that? So the Oracle challenge is that it's a tough one in fuzzing, and it's a big determiner in how effective your testing is. So sure, you can generate bad inputs, you can deliver them to a target, but how do you know if your target's failed? A really simple approach is valid messaging. So after every bad message that you send to your target, you can send a good one and look for a reply. You hit it, and then you say, hey, are you okay? And it says, I'm okay. So you hit it again, and then you just keep going that way. That'll help you detect kind of macro failures like process crashes and stuff like that. And then if you want to go more subtle, then you probably, in many cases, you'll want to have the source code so that you can instrument it in various ways. So Google's got this cool thing called an address sanitizer, which you can use. You recompile your source with it, and then it does all sorts of allocation and deallocation checking and stuff like that. There's a tool called memcheck, which is part of the Valgrind suite. And it is Valgrind. It looks like Valgrind. And that didn't sound right to me, so I finally looked it up, and it's based on some Norse god or something. So it's Valgrind. And then this last point is behavior analysis. And this is how we found Heartbleed. So what do I mean here? Fuzzing in general is, let's send a bunch of bad stuff to the target and see if it breaks. Let's see if it fails. And what we're doing here is adding a little bit of functional testing. which is, as we're doing this fuzzing, let's see how the target behaves. And if it does something that we know is wrong, we'll definitely flag that. So we call this feature Safeguard, which is in addition to our DEFENSICS fuzzer. And I really tried to go vendor agnostic with most of this, but this is the exception here. And what we're doing with Safeguard is checking for things that just obviously wrong. And I think the easiest way to understand this is, again, in TLS, to think about if we're the fuzzer and we send a client certificate to the server, and we know that client certificate is bad because we made it bad on purpose, but we still get authenticated on the server, then we know that's a problem. So we call that our authentication bypass check. And if we had just had this in place a few months earlier, and if Apple were using it, they would have found go to fail with this thing, because we'd send a bad certificate and get authenticated, and it would have been obvious. So the specific way that we found Heartbleed was through one of these checks. And it wasn't authentication bypass, it was through one called amplification. That's ironic. Amplification. And what we're doing here, the primary reason for the amplification check is to look for reflected UDP DOS attacks like Dan Kaminsky was talking about this morning. If I send one UDP packet here and a bunch come out, we'll flag that as an amplification check warning. But in TCP, which is what we were doing with the TLS testing, what we're looking at is the ratio of the sizes of the outgoing and the incoming messages. And this is kind of tricky. So what we do is, when we're doing valid messaging, just valid TLS messages going back and forth, we look at that ratio, the size of messages we're sending out and the size of messages we're getting back, and we just record that. It's like a baseline, we have a special name for it. It's like baseline amplification factor or something like that. Anyway, we record that ratio as a baseline. And then while we're doing the fuzzing, we again measure the ratio of the sizes of the outgoing and incoming messages. And if we see anything that's really out of line from our baseline, we flag it as an amplification warning. So, our development team's mostly in Finland. I don't know if you knew that. We've got maybe 100 people over there. A lot of them are developers. And I've never been to Finland. I've been working at Codenomicon for 3 years, and they keep offering. They're like, hey, you want to go to Finland? And I'm like, not too much.
You have to learn how to say University of Oulu.
Yeah, Oulu. That's where it all started. And so the winter's about 42 weeks long, right? And there's not too much sunlight, and there's not a whole lot to do. You can drink, you can code, and so they get a lot of amazing stuff done. But anyway, they were working on this feature. They were working on this amplification check, and they were implementing it in the TLS test suite. And of course, they were using OpenSSL as a target because it's so convenient, it's free, it's available. And it was chugging away, and all of a sudden the amplification check blinked on, and then that's how they noticed. And then at that point, they went digging into it, and then they discovered all the details about how it was spewing out memory and information and stuff like that. So does that answer your question?
Yes.
Okay.
I'm just wondering how this could be adapted to other kinds of fuzz testing. I mean, I happen to do a lot of fuzz testing, both with Codenomicon and other custom tools. And you're right, the Oracle is the hardest part, just finding out what.
Yes, it is. Yeah. Right. So sort of the very first basic step is you do the valid case messaging, but then as soon as you're passing all your tests there, then probably the next thing you have to do is improve your Oracle so that you're able to catch more failures and more types of failures. There's a variety of things you can do. If the target has S&P, you can go get resource usage values from S&P as you're testing and check those out. And you can run targets in a debugger again, if you have source code, and that allows you to flag failed assertions and stuff like that. So having said all that, what now? Like I said, there were really two problems, and the one problem was OpenSSL is open source, and I'm sure they do testing. I'm sure there's a whole test suite involved with that, but it's probably mostly functional or entirely functional positive testing. And the people who were using OpenSSL basically had that mindset of, well, this isn't really our code, so, and everybody else is using it, so it's probably okay, so that's fine. So that was one problem. And then the other problem was the tools are evolving. You know, this is a fast changing part of our world. And I think as an industry, we're waking up to the fact that better software testing has to take place. But it's evolving fast, and I think the tools are just always evolving and getting to the point where they will find something like this. So probably the best advice I can give to you is keep current. You know, keep your eye on the ball, keep your tools up to date, and always be as current as you can with the way that you're looking for vulnerabilities in your software. And that's all I had. So at this point, any more questions I'd be happy to handle. Yeah?
When you detected the OpenSSL bug through the fuzzing techniques, how helpful was it to just narrow it down? Did you just all of a sudden know there was a bug and it took weeks, days, months?
It was actually very quick because as soon as the engineers had finished coding this amplification check, it popped on OpenSSL. And then once you went and looked at the test logs, it was pretty apparent what was going on, because you could see we were sending out this little heartbeat where we had lied about the length of our message, and we were getting back a big response. And I think pretty much just by eyeballing that response, they were able to recognize that they were seeing memory from the server.
You know how Google detected it?
I don't, and I've been wondering that, and I've been looking around for it, and I can't find a thing. So all I know is the guy's name, Neil Mehta, and I would kind of assume that, well, never assume, right? I would kind of assume that he was actually doing a source code audit, but I cannot find any information about it, and they've been very quiet about it.
I hear some people south of here learned about it a long time before this. Some of the NSA or something like that.
Yes, it's possible.
What's the question?
He's heard that some people in the NSA may have found out about it before, but, you know, I have no comments on that.
They don't share.
There have been some people who have looked at net traffic, recorded net traffic over the last 2 years when the vulnerable versions of OpenSSL were out there, who have seen no indication that anybody had tried to exploit it. Anyone else? Okay, thank you very much.